When you include the squared terms or interactions, it complicates the estimation of the effects. Suppose we're interested in what determines income. Consider this model with squared terms. For each individual I, income is their annual income in dollars, education is their number of years of education, and epsilon is the error. This is the partial derivative. The partial effect, or marginal effect, of an additional year of education depends on the level of education. The benefit of additional education may be less for someone with a master's degree compared to someone with only a high school diploma. One thing you might want to know is the average effect across all levels of education. This is called the average partial effect, APE. Why is it important? It summarizes a potentially complex derivative into an economically meaningful number. Suppose you're presenting your research to the government. You could explain that income increases by an amount equal to beta 1 plus 2 multiplied by beta 2 multiplied by the number of years of education. Alternatively, you could state that on average, income increases by $10 per additional year of education. This makes the findings more accessible and easier to understand. The same issue arises when the model includes an interaction term. For each individual I, income is their annual income in dollars, education is their number of years of education, experience is their number of years of experience, and epsilon is the error. This is the partial derivative. The effect of an additional year of education depends on the number of years of work experience. We can calculate the APE in several ways. Let's consider a model that includes squared terms. One method is to calculate the marginal effect for each observation and then average these effects across the sample. This approach shows how income would change on average if each person's education were increased by 1 year. Another method is to calculate the marginal effect at the mean values of the variables, specifically for a person with the average number of years of education in the sample. A direct way to estimate the APE is through reparameterization. We reparameterize the variables to be centered at their means. The partial derivative is now given by this formula. Beta 1 is the effect at the average level of education. When education is at its mean, the second term drops out, leaving beta 1. We can perform a t-test on beta 1 using the associated standard errors. Similarly, we can reparameterize a model with interactions by centering the interaction term at the mean. To do this, we create two new variables: years of education minus the average number of years of education, and years of work experience minus the average number of years of work experience. Adding or subtracting a constant from regressors does not influence the linear regression model, as the constant doesn't affect the partial effect when taking the derivative. The partial derivative is now given by this formula. Beta 1 is the effect at the average level of education. When education is at its mean, the second term drops out, leaving beta 1. We can perform a t-test on beta 1 using the associated standard errors. Often, we're interested in the average effect. However, sometimes you may want to know the effect at specific values. For instance, you might be interested in understanding the effect for a person at the top quartile of education, which places them in the top 25%. In such cases, you'd substitute the top quartile value into the derivative formula. Similarly, during reparameterization, you can use the top quartile value instead of the average. For more lessons on econometrics, visit alphas&betas.org.